So we're going to be learning about absolute value functions today. We're going to be translating graphs of absolute value functions, stretching, shrinking, and reflecting absolute value functions, and combining transformations of graphs of absolute value functions. An absolute value function is a function that contains an absolute value expression. The parent absolute value function is f of x equals the absolute value of x. The graph of f of x equals the absolute value of x is v-shaped and symmetric about the y-axis. The vertex is the point where the graph changes direction. So the vertex is right here. Okay, it's either going to be the lowest y value or the highest y value. The vertex of the graph of f of x equals the absolute value of x is 0, 0, as we see here. The domain of f of x equals the absolute value of x is all real numbers because you can plug anything in for x. And the range is y is greater than or equal to 0, which makes sense because we can't have a negative number pop out of the absolute value expression. The graphs of all other absolute value functions are transformations of the graph of the parent function f of x equals the absolute value of x. The transformations presented in section 3.6 also apply to absolute value functions. And if we just take a look at the graph right here, if we just had f of x equals x, it would just be a line, and we'd have our negative outputs here. But remember, we can't have a negative output with this absolute value. So if I have a negative 2, for instance, the output of negative 2, well, the absolute value of negative 2 is positive 2. So that's why it starts going up at the vertex here. Graph each function. Compare each graph to the graph of f of x equals the absolute value of x. Describe the domain and range. Well, if we see our graphs down here, the absolute value of x is graphed for both of them, which is great. So we just have to graph this right here. So there's multiple ways to graph, but in this example, we're going to be making a table of values. So I'm making my table. And I think it's good to have 5 different points. And like I said, I'm going to show you another way how to graph these functions later in this video. But I'm going to plug in 0, 1, 2, and then negative 1 and negative 2. Okay, so when I plug in my values, I get negative 2. Well, the absolute value of that is positive 2, plus 3 is 5. And then if I plug in negative 1, I get positive 1 in the absolute value, plus 3 is 4. Plug in 0, this whole term drops out, I just get 3. And then if I plug in 1, well, the absolute value of 1 is 1, plus 3 is 4. And then I'll plug in 2, absolute value of 2 is 2, plus 3 is 5. Okay, if you notice, at 0 right here, this is symmetrical. At my vertex point, my y values are symmetrical. Okay, so I'm going to just plot these points. So 0, 3, 1, 4, 2, 5. Then I have negative 1, 4, and negative 2, 5. Now I'm going to draw my absolute value function through this. So I've drawn my absolute value function, and notice that all I'm doing here is I'm taking my original parent function and just translating it 3 units up. Every single point on this is just 3 units below my new function g of x here. And that makes sense because I see that I have a plus 3 outside of my original function here. So that means a vertical translation 3 units up. Now I need to describe the domain and the range. Well, the domain is unaffected. I can still plug in any number for x. The domain is still going to be all real numbers. So I write that down here. And then the range, well, normally the lowest value to come out of the absolute value function is 0, but now the lowest value is 3. So whatever your y value of your vertex is, that's going to be either your lowest or your highest absolute value function, depending on whether or not there's a vertical reflection. But anyway, I'm going to write that. So this is going to be y is greater than or equal to 3. And now we're done with part A. For part B, I'm going to make another table. And I'm going to use a trick to find our vertex pretty easily. So this entire expression inside the absolute value operation, x minus 2, when this whole thing is equal to 0, that is going to be my x value of the vertex. So I'm going to set x minus 2 equals 0. If I add 2, I get x equals 2. So that's the point I'm going to put in my middle. And then I'm going to surround the rest of these points. So 3, 4, 1, and 0. And if you're not sure why that is, just imagine. If this value is 0, that's the lowest number that's going to come out of an absolute value expression. It's 0. Because if you had a negative number in here, it would turn positive. And if you had a positive number in here, it would turn positive. So setting this whole thing equal to 0 will find our vertex every single time. So I'm going to plug these values in to get my y values. So I'm going to take the 2. 2 minus 2 is 0. Absolute value of 0 is 0. And then for 3, 3 minus 2 is 1. Absolute value is 1. For 4, 4 minus 2 is 2. Absolute value of 2 is 2. And because I know this is my vertex, these y values are going to be symmetrical. So this is going to be 1, and this is going to be 2. Okay? And you can plug these in to figure that out. Like 1 minus 2 is negative 1. Absolute value of that is 1. And then the same thing will happen here to get to 2. Anyway, I'm going to plot these points and then graph. And maybe I'll use a different color. I'll use red. So anyway, 2, 0 is right here. 3, 1. 4, 2. Fix that point. And then I have 1, 1 right here. And 0, 2. Now I'm going to draw my absolute value function through this. So now that I've graphed my new absolute value function, m of x, I see that all I've done is I've slid this whole thing to the right, aka I've translated this, my original parent absolute function, 2 units to the right. And we can tell that actually because this x minus 2, this minus 2 is on the inside. Remember, on the inside we kind of reverse things. So moving 2 to the right is actually negative, and moving 2 to the left would be positive. So this is going to be a horizontal translation 2 units to the right of our original function. And now we want to talk about the domain and range. So draw a box here. So anyway, domain, it's still unaffected. I can still plug in any number that I want, so that's going to be all reals. And then for my range, well, I didn't change my y value at all. So my lowest y value is still 0. So I can just have any y value that is above or equal to 0. And now we're done with this one. In this example, we're going to graph each function and then compare each graph to the graph of f of x equals the absolute value of x. Then we're going to describe the domain and range. All right, so in the last example, we made tables to graph. This time, I'm going to show you how to graph using the vertex. So I'm going to zoom in on part A right here. Well, remember, I said earlier that we know the vertex is going to be at the point when this entire absolute value expression on the inside equals 0. So I just have to set x equal to 0 here, and I know that's going to be my vertex. So I know my vertex is at x equals 0. So I'll do my new point, my new graph in red. Okay. Well, now I know that I have this 2 on the outside, and this 2 is going to represent our slope. Okay. Now, when x is greater than or equal to 0, our slope is going to be positive 2. Okay. So I can just use my rise over run. I can go up to right 1, up to right 1, up to right 1, and so on. So that's what I'll do. But over here, on the other side of the y-axis, my slope is actually going to be negative 2 because we know that the absolute value is a v-shape. Okay, another way you can think of this is I'm just multiplying all the values that are coming out of this by 2. This is then going to be a vertical stretch. Okay, but since it's on the other side of the vertex, my slope is going to just be the opposite, which in this case is going to be negative 2. So I'll go up to left 1 in this case, I'll keep doing that up to left 1. Okay, now I'm going to draw my absolute value function. So now that I've graphed my absolute value function, let's compare it to the original function, because I believe that's what it says up here. Yep. So once again, if I see, I've vertically stretched this, okay? Each of my points, I can pick any point on the original graph, and then all I'm doing is I'm multiplying that y value by 2. So here, I go from 1 to 2. Here I go from 2 to 4. Here I go from 3 to 6. So this is my vertical stretch. You can do the same thing on the other side of the graph. So once again, a vertical stretch, I'm stretching the function away from the x-axis. Now I need to talk about the domain and range. Well, I can plug any number in for x. So my domain is going to be all reals. All real numbers. And the range is going to be anything larger than 0. Because in this graph, you can kind of tell the vertex is 0, and I can't do anything below that because nothing can pop out of an absolute value that is negative. So anyway, it's just going to be y is greater than or equal to 0. And now we're done with part A. For part B, I'm going to look at this graph, and we'll do this in the same way. Once again, you could make a table with any of these, but I just want to show you guys all the different ways, and then you can pick which one that you want to do the best. I prefer doing this method over the table because I think it's a little bit faster, but the table will always get you the right one anytime. So I look to see p of x equals negative 1/2 of the absolute value of x, and I see that I have a 1/2 on the outside of this function, and I have a negative sign on the outside of this function. Okay, and this means that I am doing a vertical shrink by a scale factor of 1/2. Okay, and I can figure that out because it's on the outside of the function. Any vertical change happens on the outside of the function. This negative is going to be a reflection in the x-axis because remember, a reflection in the x-axis is a vertical change. I'm going from the top or above of the x-axis to below the x-axis. I'm going from up to down, and that's a vertical change. So anyway, I want to find my vertex, and once again, it's still going to be the x value of the vertex is going to be 0, so it's going to be the point 0, 0. So I'll plot that point. Okay, and now I know that my slope is going to be the number multiplied by x, and in this case, it's going to be 1/2, but because I'm reflecting this, I'm flipping this. So if there was no negative sign, it would go like this. It would still be above the x-axis, but since the negative sign is on the outside of the absolute value function, this is going to be below the x-axis. So when x is greater than or equal to 0, my slope is going to be negative 1/2. So I'm going to go down 1, right 2. And then when my x is less than 0, I'm going to have a positive 1/2 slope. So I'm going to go down 1, left 2. Now I'm going to draw my absolute value function. So now we want to compare the graph to the original graph, so my red one to the black one. Okay? And like I said, we can tell from the equation, but this is going to be a reflection in the x-axis and then a vertical shrink by a factor of 1/2. And now I'm going to talk about the domain and range. So the domain, once again, is all real numbers because I can plug in any x value here. The range this time is going to be a little bit different. The range is going to be y is less than or equal to 0 because if we see, there's no positive numbers on this red graph right here. Okay, the highest number is 0, so that means all the y values are going to be 0 or lower, which is this. All right, and now we're done with this one. Vertex form of an absolute value function. An absolute value function written in the form g of x equals a times the absolute value of x minus h, all plus k, where a is not equal to 0, is in vertex form. The vertex of the graph of g is h comma k. Any absolute value function can be written in vertex form, and its graph is symmetric about the line x equals h. Okay? Now, remember what I said earlier. This x minus h, anything inside of the absolute value expression, if we set that equal to 0, we'll get our vertex. Okay? So if I do x, if I do x minus h equals 0, I add h on both sides, I get x equals h. Okay? So if I plug in h here, this whole entire term comes off because I get a times h minus h in the absolute value. Okay, but this is just 0, so this would become 0 times a, which that whole term would drop out, and all I'd be left with was k. So my input is h, my output is k. So we're going to use this to help us graph absolute value functions. Graph f of x equals the absolute value of x plus 2, all minus 3, and graph g of x equals the absolute value of 2x plus 2, all minus 3. Compare the graph of g to the graph of f. So first, I'll graph f of x. So once again, you could always make a table, okay? But I think it's easier to use the method that we used in the last example, so I'm going to do that. So I have x plus 2, and then I have this minus 3. So if you remember, I can identify my vertex right away. My vertex value is going to be negative 2 because x minus h, that gives us h, but I have a plus 2 here. So the way to get from positive 2 would be x minus negative 2. Either way, I know that my vertex is going to be the ordered pair negative 2 comma negative 3. Once again, if you're ever unsure, you can just set whatever's inside equal to 0. If you did x plus 2 equals 0, you'd subtract 2, and you get x equals negative 2. And then you just plug that back in, and you're going to get this k value. Anyhow, I know this is my vertex, so I'm going to plot this. So I'll go negative 2, negative 3, so right there. I'll plot this one in black. Okay, now I want to see which way this is going. Okay, well, first of all, there's no coefficient on my x, either on the inside or the outside. So the slope is going to be either 1 or negative 1. And there's no negative sign reflecting this. So I know it's going to be in a V shape. So to the right of this point, it's going to go, it's going to have a positive slope. And then to the left, it's going to have a negative slope. So I'm just going to plot that really quickly. Now I'm going to graph g of x. So if you notice, the only difference between g of x and f of x is now I have a coefficient of 2. The rest of it is the same. Okay? Well, this 2 being multiplied by x on the inside represents a horizontal shrink by a scale factor of 1/2. Remember, when we're dealing with the inside of the function, we reverse things. It's kind of backwards. So the scale factor is not 2. It's the reciprocal of 2, which is 1/2. Anyway, so you could graph it like that, just basically bring all of these x values closer to the y-axis since we're kind of compressing it in. So if you did it that way, I'll do that in green, we would just move everything halfway towards our y-axis. So this would be right there, right there. This would stay the same. And I'll do it on the other side as well. So if you notice, all these green points are halfway towards the y-axis than the black ones. Now this way might be a bit hard to grasp because you might not necessarily notice right away that there is a horizontal shrink with a scale factor of 1/2. Okay, so I'm going to show you another way that will work every single time. So I'm going to erase all these points. I'm going to move f of x over. The way we're going to graph g of x is by just finding the vertex. Remember, the vertex x value is just, if I set 2x plus 2 in this case, the inside of the absolute value operator equal to 0. Okay, so I get 2x plus 2 equals 0. Subtract 2. 2x equals -2. Divide the whole thing, both sides, and I get x equals -1. Okay, so now my new vertex is -1, which makes sense because if I'm compressing it by a scale factor of 1/2, my x value is just going to move closer towards the y-axis. I'm cutting the distance in half. Okay. Anyway, now this right here, x equals -1, is my new input for the vertex. So I'll plug this back in and find the output for the vertex is going to be -3. Because if you plug this back in, well, we know that this is the value that makes 2x plus 2 equals 0, because I have 2 times -1, which is -2, plus 2, that's 0. So this whole entire part will drop out, and my y value will be -3. Okay, so I'll plot that in red. This is the point -1, 3. That's how to find the vertex. Okay, and now I'm just going to use the same thing. Okay, well, the coefficient here of my x term is 2. Okay, and at this point, it doesn't really matter whether or not it's inside or outside of the absolute value. Okay, so now I want to see if I have any reflections. So I don't have any negative sign either on the inside or on the outside here. So that means that it's going to still be a V shape, okay? But I see that since 2 is being multiplied by x, my slope is going to be either 2 or -2. And since I want to keep that V, when my value of x is greater than my x value at the vertex, so -1 in this case, then I'm going to go up and have a positive slope. And when it's less than -1, I'm going to have a negative slope. So here I'm going to go up to right 1, up to right 1, and so on. And then to the left of -1, I'm going to go up to left 1 to show that I have a negative slope. Now I'm going to draw my absolute value function. And if you look back at this video, all these points on the red function were on that green function that we graphed earlier. It's the same thing, just 2 different ways to do the same thing. Once again, you can always make a table of values, but it's important to be able to find the vertex in order to know where to start your table of values, where to have that middle value. And that's what we did up here, setting 2x plus 2 equal to 0, because that's what's inside the absolute value function. Okay. Now I'm just going to write down the transformations because it asks us to compare the graphs of g to f. Okay. So like I said, we know that all we had to do to get from f to g is a horizontal shrink with a scale factor of 2. So I'm just going to write that down here. Horizontal shrink with a scale factor of 1/2. Remember, because we have to take the reciprocal of 2, which is being multiplied by our x inside the function. And now we're done. Let g of x equal -2 times the absolute value of x minus 1, all plus 3. Describe the transformations from the graph of f of x equals the absolute value of x to the graph of g. Part B, graph g. Okay, so I'm going to zoom in on the actual equation for the function g of x. And I see a couple of things going on. Okay, I see I have this -1 inside of the absolute value. Then I have this +3 on the outside, okay? And I know the -1 on the inside represents a horizontal translation 1 unit to the right, because remember the minus is reversed, okay? If I wanted to go to the left, I'd do +1, okay? And then on the outside, this is +3, so that's going to be a vertical translation 3 units up, okay? On the outside, it's not backwards like it is on the inside. Okay. I also see a negative sign on the outside. This negative sign on the outside tells me that there's going to be a vertical change for my reflection. So this reflection is going to be in the x-axis, because if I look at my graph here, if I go from vertical change, so if I start on the top and I go to the bottom, or I start on the bottom and go to the top, that's a vertical change. The x-axis is acting as my mirror. And then I see this 2. This 2 is going to be a vertical stretch because it's on the outside of the function. Okay, and so my scale factor is going to be 2. So anyway, I'm going to write all those down. We have a translation. And that was 1 unit right, 3 units up. I'm reflecting in the x-axis, so reflection in the x-axis, because that's what's acting as my mirror. And last, but definitely not least, we have a vertical stretch. And my scale factor is 2. So with a scale factor of 2. Okay, so right from the equation, I can tell all of the transformations that are going to happen from my original parent function. Okay, now I'm going to graph this. Okay, I'm going to use the same method that I've been using for the last couple of examples. I'm going to find my vertex, which I can tell right away what it is, and then I can graph using the other information. Okay, so right away I know that my vertex is going to be 1, 3, 1, 3, that point, because if I plug 1 in here, this whole thing goes off, becomes 0, and then my y value is 3, okay, and 1 is the value that makes this inside become 0. So there's my vertex. Okay, now I want to see, okay, is this going to be a V shape or is it going to be an upside down V shape? Okay, well, the negative sign out here makes me know for a fact that it's going to be an upside down V. Okay, if it was positive out here, it'd be a V, but it's negative, so it's going to be upside down V. And then my slope is either going to be 2 or negative 2. And because it's going to be an upside down V, it's going to look like this. When x is larger than 1, my vertex value, okay, it's going to have a negative slope. And then when x is less than 1, it's going to have a positive slope. Okay, so like I said, it's going to be either 2 or negative 2. So for the first one, I'm going to go down 2, right 1, and then keep doing that. And I like to have all my points go all the way until I can't fit any more on the graph. That's going to give me the most accurate one. And then over here, I'm going to do down to left 1. All right, and now I'm just going to draw my absolute value function through these points. So I have successfully described the transformations from the graphs, and I've graphed it. So now we're done with this one.